Back to our problem that we set up at the end of the last video. We've got a helicopter that has two kind of periods of its motion. First, it rises at a constant speed of 7.2 meters per second until it reaches a height of 115 meters. Suddenly, the engine stops and the helicopter goes into free fall. And it doesn't just immediately start dropping. Of course, when the engine cuts out, it's going upwards and it continues to go up until it reaches some maximum height. That's probably not a very big distance it goes, but it does take a moment to come to a high, it goes above 115 meters before it momentarily comes to rest and starts to fall down. So there are two different regions of the motion or time periods. One is the constant velocity or zero acceleration motion for that first 115 meters, and the second part is in free fall. Okay, so the first question we want to answer is how long does it take the helicopter to reach the height of 115 meters? Now, for this particular problem, you could just go back to what everybody learns, back in high school or junior high. I'm not sure when you learn it, but the old formula, if something's moving with constant velocity, distance equals speed times time. In this case, the thing is moving with constant speed, so I can use distance equals speed times time. That comes out of the kinematics equation, so I'm actually going to show how to do it using the kinematics equations. And always when we use them, we want to be very definite about our axes and our time. So let's take y equals 0 to be the ground and plus y to be up. That means our ay, at least if I keep this convention down below, ay would be minus 9.8. Now in this first period that we're talking about here, ay is 0, okay? Let's also take t equals 0 to be when it leaves the ground at that constant speed, okay? And in this case, I didn't say it on here, but it seems to make sense because we're asked about how long it takes in time to reach that 115 meters. The final time will be defined by when it reaches a height of 115 meters, okay? And let's take one of our kinematics equations. We want to know the time, and we know something about the initial velocity, and we know the constant acceleration, and we want to know the time, and we also know the distance that it goes in between y initial and y final. So it sounds like we want something that relates the distance y to the time t and solve for t. That's this equation. And I have to apologize for this scan here. For some reason the scan is excessively blurry, but hopefully you can decipher it. Y equals y0 plus vy0 times t, that says, plus 1/2 ay t squared. And this, I know it's a little bit cryptic there, this is an arrow with a 0 pointing to the ay. Ay is 0 if we take the time period from when it leaves the ground to when it reaches 115 meters. It's not accelerating at all. Of course, when something leaves the ground, it can't just leave, it's at rest on the ground, it can't suddenly have an upward velocity, but we're making kind of an idealization here. We're going to pretend all of a sudden it leaves the ground at 7.2 meters per second and there's no startup time that's required. Okay, so our goal is to solve for t. Thankfully, this t squared term goes to 0 because ay is 0 all the way between what we call t initial and t final, which is when it reaches 115 meters. So I can plug into the remaining parts of the equation. Y final is 115 meters. If it starts out at y equals 0, when it goes up 115 meters, it's at y equals 115 meters. Y initial is 0. Vy initial is plus 7.2 because plus y is up. That has a t sitting next to it. I know it's a little blurry. And we already said this third quadratic term is 0 because ay is 0. So all I need to do is solve for t. And notice this reduced down to distance equals speed times time. So if you fell back on that old formula, as long as you know something's moving at constant velocity, no problem, you can go back to that. But it comes out of the kinematics equations. We can solve for t and we find out t is 15.97 seconds. So it takes about 16 seconds. Again, we said be reasonable, 3 sig figs. So here I've said 1, 2, 3 sig figs was a reasonable answer. Out of my calculator, I wrote down 4, but then I rounded to the third place. Since this is 5 or larger, I rounded up and made this a 16.0. All right, part B. How long after the engine cuts out does it take the helicopter to crash to the ground? Notice this is a different time period, and so the helicopter is essentially in free fall now since we're ignoring air resistance, if you read the statement of the problem at the top. So we want to know how long it takes, and we know its initial velocity, right? It was going at 7.2 meters per second right when the engine cut out. So I'm going to call that time, we'll take, well, again, so some conventions I'm showing over here on the right-hand side for this. Second time period, we're going to take y equals 0 to be the ground and plus y to be up, just like we did before. But now we're going to take t equals 0, and I know that's faded out there. T equals 0 to be defined by the moment at which the engine cuts out. So that says t equals 0 at cutout. And we want to know the time it takes to get from y equals 115 meters down back to y equals 0. And so we know something about y initial and y final, and we want to know something about the time it takes to get from y initial to y final. And so the kinematics equation that relates those two is the same one we used above, the y versus t quadratic equation there. And plugging in what we know, we're going to say initial is when the engine cuts out, and final is when it hits the ground. So y final is 0 because then it's on the ground. Y initial is 115 meters. Vy initial is 7.2 because at the moment the engine cut out, it was going upward at 7.2 meters per second squared. Times t plus 1/2, and it's in free fall now. We've chosen plus y to be up, so ay is minus 9.8. 1/2 ay times t squared. Unfortunately, so we do want to solve this. We know everything in this equation except t. The unfortunate thing is we have a quadratic equation here. And there are always ways in these physics kinds of kinematics problems to avoid using the quadratic formula. But I'm calling this method 1 because we're just going to attack this problem head on and use the quadratic formula, which I'm assuming all of you learned sometime in high school, in your high school algebra course. So if you have the quadratic formula, I didn't write it down here in my solution, but the quadratic formula says if you have something of the form at squared plus bt plus c, then the solution is, there are two solutions to that, and they are t equals negative b plus or minus the square root of b squared minus 4ac, that whole thing all over 2 times a. You can look it up if you want, or we can practice it more in class. We won't be emphasizing this too much in Physics 110, but you will find some homework problems where you've got to use the quadratic formula to solve them. Okay? In our case, the solutions for the t's are t equals negative b, so negative 7.2, plus or minus the square root of b squared, that's 7.2 squared, minus 4 times a, and our a is 1/2 times minus 9.8, so our a is minus 4.9, times c, and our c is 115. All of that mess over 2a, and that's 2 times minus 4.9, that should say right there. And I can plug those two values into my calculator, either using the plus or the minus, and get two values. It seems like a waste of time to calculate both of them if you can tell which one is going to be the larger one. In this case, I expect that, if this object were in free fall for a long time, it would have, if we call t equals 0 when the engine cut out, if we imagine it were in free fall before that, there would be a negative time at which it would have been at t equals 0, and we're interested in the later positive time at which it's back at y equals 0. And so I'm interested in the larger of the two times. And it's a little bit confusing here, but you can see that ahead of time by noting that the denominator is negative. And so when I have the plus or minus sign here, because the denominator is negative, if I take the negative sign up here, I will actually be adding something positive onto this initial number right there, and that will give us the larger one. So we're going to use the minus sign, but you could plug them both in and see which one is the larger time. In this case, I say take minus sign for the positive t, and that gives us t equals 5.63 seconds. Now, I want to do this using a second method, which avoids the quadratic formula, and you can always avoid it if you're clever enough doing these kinematics kinds of problems. So, same convention, we're going to take y equals 0 at the ground, plus y is up, t equals 0 at cutout. But instead of going directly to this equation that gives us, subs in what we know and has what we want to know as a variable, I'm going to go to a different kinematics equation, that third one, Vy final squared equals Vy initial squared plus 2ay times delta y. And I don't know anything about Vy final. That would be the y velocity just before it smacks into the ground, like right before it contacts the ground. I don't know anything about that, and I don't want to know anything about it, but I'm nonetheless going to solve for it here, and we'll find that we can avoid using the quadratic formula by doing that. I know Vy initial, that's still plus 7.2, and I know Ay is minus 9.8, and I know that if initial is when the engine cuts out, and final is when it hits the ground, it's gone downward in y by 115 meters, so delta y would be minus 115. So substituting those in and then taking the square root of both sides, I would get the magnitude of the y velocity when it hits the ground, I know it's going to be negative, is the square root of the stuff that's on the right-hand side. 7.2 squared plus 2 times minus 9.8. And it's absolutely crucial that you get that minus sign in there. Otherwise, you might be taking the square root of a negative number. So in this case, when I calculate that, I get Vy final. That's the y velocity right before it smacks into the ground is 48 meters per second. And, Vy would actually be minus 48 because Vy final, because plus y is up. So if I then go to this equation, which is not a quadratic equation, but a linear equation that tells us if I know Vy final, I could solve for t in between initial and final. Vy final in this case is minus 48 because it's going downward and plus y is up. Vy initial was plus 7.2. That's when the engine cut out. It was going upward at 7.2 and very quickly starts slowing there. And Ay is minus 9.8. The only unknown in that equation is t, and I could put the numbers in my calculator and solve for t. You get exactly the same t as we did using method 1. It's not clear which one's easier. It depends on how much you like the quadratic formula. But here I've turned it into a kind of a two-step problem. Over here it was a one-step problem, but I had to think about the horrendous quadratic formula. And I also have the danger, which is probably the greatest danger of using the quadratic formula, that in putting this stuff into your calculator, you're going to make a mistake because the quadratic formula is so complicated. It's somewhat simpler to do these two steps, even though it is a two-step problem. Get the same time in either case. All right, the third question is how long after the engine stops does it take for the helicopter to reach its maximum height? So here I'm interested in not how long it takes to get from engine cutout to ground, but rather from engine cutout to maximum height. And so I'm going to take t equals 0 at cutout, and I'm going to take t final, that t, to be when it reaches maximum height. Same conventions for y, plus y is up, y equals 0 at the ground. And so I want to know t, and I do know something about the final y velocity. When it reaches its maximum height, its y velocity at that moment would be 0. So it seems like I know something about Vy final, and I want to know something about t. Let's take the relationship, the kinematics equation, that relates Vy final to t, and substitute in what we know and hope for the best. Vy final is 0, because final means when it reaches its highest point, it's momentarily at rest there. Vy initial was plus 7.2 because plus y is up, and Ay is minus 9.8, and I can solve for t. That's 0.735 seconds. So when the engine cuts out for 0.7 seconds after that, it's still rising before it comes to a maximum height and then starts falling down to the ground. All right, that was, this is closer to the kind of thing you'd be doing in the homework or maybe on an exam or something like that. A lot of times I try to avoid the quadratic formula on exams, but other than that, the general difficulty of this problem, setting things up, is more typical of not introductory problems on kinematics or free fall motion, but the kind of thing that you're expected to do after you're comfortable with it in the course. We'll practice a lot more with it. Okay, let's finish up this chapter's material with just a couple of, I think, 3 voting questions. First one says, if you drop an object in the absence of air resistance, it accelerates downward at 9.8 meters per second squared. Of course, that's free fall. If instead you throw it downward, so I'm comparing just dropping a rock from rest to taking a rock and throwing it downward, just after I release it, what is its downward acceleration if I throw it really hard in the direction downward, but we're still ignoring air resistance? Less than, equal to, or greater than 9.8. If you need more time to think, just pause the video. The correct answer is here, as long as we can ignore air resistance, I haven't thrown it so hard that it's really getting blasted by the wind, then the acceleration is the same. That object, that just like when I throw something upward, we saw in the little cartoon, it's in free fall as soon as I release it from my hand. It's the same is true if I throw it downward. If I throw something downward, I might have just released it from a little height above there, and it would have been going downward by itself a little time later. So throwing it downward is sort of the same as releasing it from a higher point from rest. So as long as air resistance is negligible, the acceleration is 9.8 in the direction downward. Doesn't matter what its velocity is or what its position is, as long as it's close to the surface of the Earth. Second question. Person standing at the edge of a cliff throws one ball straight up and another ball straight down with the same initial speed. So I do an experiment where I have 2 balls, one thrown up at 3 meters per second, one thrown down at 3 meters per second, and we can ignore air resistance in their subsequent motion. So if we ignore air resistance, which ball hits with the greater speed when it hits the ground? The one thrown upward, the one thrown downward, or neither? Of course, the one thrown upward will take longer to get down to the ground. We don't care about that. But when they do hit the ground, which one has the greatest speed right before hitting the ground? All right, this question always generates some controversy when I've used it in class before, and we usually have a lot of discussion about it. And there are usually quite a few people on both sides of it, in all 3 answers, I would say. The correct answer is they hit with the same speed. One way to see that, I don't think I have a copy of the kinematics equations here, but let's just scroll back so that we can look at one of the kinematics equations. Here we go. And I'm going to imagine I want to compare, so the ball I threw down has a certain velocity. The other one I threw up with a certain velocity. My question I'm going to answer in order to know the answer is, after that ball I threw up goes upward to its maximum height and comes back down and passes where its release point was, if it has the same velocity as the one that was just thrown down initially, then they've started with the same condition. They're going to hit the ground with the same speed. If it's going more slowly, then it's going to hit the ground more slowly. And if it's going more quickly, then it's going to hit the ground more quickly than the other one. So I want to find, if I release it from a certain height, the one that's going upward, what is its speed when it passes that same height on the way down? And conveniently enough for me, this third kinematics equation that happens to be boxed here is the one we want to use. We can think of initial as right after I release it from my hand, and final is when it has gone up and back down is passing where the release point was on the way down. That's what final means. So notice that in this case, and what I'd like to know is what Vy final is. Is Vy final equal to Vy0, or is it bigger or smaller? Notice that if I take initial to be release and final when it passes that same point on the way down, delta y is 0. Its displacement is 0 between the release point and when it's gone up and down and passes the release point again, delta y is 0. So this goes to 0 right here. We can just X that out, and that means that Vy final squared is equal to Vy initial squared, which if you take plus or minus the square root of that, that says that Vy final is plus or minus the square root of Vy initial. In other words, they have the same magnitude. Sure, one's going up and one's going down, but their magnitude is the same. So the one I threw up, if I throw it up at 3 meters per second, when it passes my hand on the way down, it's going down at 3 meters per second. That's exactly how I release the other one. And if air resistance is negligible, they're both going to hit the ground with the same speed later on. So the forgot I was so far back here. Got to go way forward. Here we are. So they both hit the ground with the same speed because when I throw a ball up, if air resistance is negligible, if it's in free fall, it passes the release point on the way down with the same speed, and therefore it's just like the one that we threw down. All right. Finally, you throw a ball straight up in the air. At the highest point, which of these is true about the ball's velocity and acceleration? Velocity and acceleration are both 0 at the highest point. Velocity is non-zero, but acceleration is 0. I guess we have all possibilities here. Which one is true at the highest point while it's in free fall? All right, the answer is the acceleration is non-zero because when it reaches its highest point, it's still in free fall. And we said the whole time it's in free fall, on the way up, at the highest point, and on the way down, its acceleration is 9.8 meters per second squared toward Earth. So the acceleration is definitely non-zero at the highest point. But at the highest point, by definition, it's momentarily come to rest. So its velocity is 0 at that point. All right. I believe that's the end of the video and the end of this chapter material. So we'll be doing lots of problem solving practice with the kinematics equations and free fall kind of stuff in class, as well as practicing with drawing those position, velocity, and acceleration graphs. Those take a lot of practice, so that's what we'll be spending our time on in class.